state one of the most important definitions of linear algebra. So let's let V be a vector space. And let's let B be a set of vectors from V. Then B is a basis of V if 1, the entire vector space is the span of these vectors. So any vector in this vector space is a linear combination of these vectors, and 2, these vectors are linearly independent. We'll talk in depth about bases. They are, as I said, very important and form the foundation of the next few sections. For now, let me give a few examples. This first example is phrased as a theorem. It says the columns of any invertible n by n matrix are a basis of Rn. Proof. That's that A be invertible. Then AX equals B always has a solution. In particular, X equals A inverse. B is a solution. So remember that AX is a linear combination of the columns of A. So this statement says that every vector B is a linear combination of the columns of A. In other words, the columns of A span Rn. What about uniqueness? Well, not only does AX equals B always have a solution, it always has a unique solution. X equals A inverse B. So AX equals 0 has a unique solution. In particular, the inverse times the 0 vector, which equals the 0 vector. So again, remember what we have here is a linear combination of the columns of A. And what I'm saying is that the only way for a linear combination to equal 0 is if all of the coefficients are equal to 0. That's this unique solution. In particular, if you remember the elementary vectors E sub 1, E sub 2, and so on, these are called the standard basis of Rn. And they're definitely a basis because they're the columns of the identity matrix I, and the identity matrix I is surely invertible. One last example. Let's now look at P sub n, the space of all polynomials of degree less than or equal to n. This has a basis of the following polynomials. I mean, it's hopefully pretty clear that more or less by definition, any polynomial of degree less than or equal to n is a linear combination of these things. And it's hopefully also clear that these are independent. This is the standard basis of Pn. You can see it from this theorem, but I'll point out explicitly that bases are not unique. They're any vector space that has a basis has an infinite number of bases, but some bases are nicer than others, hence they get these special names.